So now we've drawn the board outline for our LED project for the Game Boy Advanced. What we're going to do next is start to think about the hardware side, making the circuit diagram, so the schematics. The first step to that is to understand what's going to happen, so we know in our mind what we're about to create. Now, if I was going to make just an LED board that literally just solders to the console and the buttons light up, that's fairly boring and basic, and anybody can do that. You're not really learning anything, you're not doing anything, and it's not a very fun project. That's why I didn't bother making LED boards in the first place. So we're going to have two versions, because people do just like LED boards lighting up. It's that simple. People love lights. But there's also a full RGB LED project to be had as well. So one where you can configure and change all the lights to any colour you like, turn them on and off, have effects, the whole works. But really, there's a lot of people that don't want to pay for that extra, and there's people that want basic lights. So we really want two projects. The first we're going to do is the LED basic project, and then we'll do the Pro project that uses a microcontroller to control the LEDs. This is all going to be open source, so you can all use this, copy it, make products from it, do what you like. The purpose is to learn it. But the first thing we're going to do is the basic LED project. So instead of just having the lights come on when you turn on the console, I was trying to think of something in between a full-blown MCU project and a basic LED project. And what we're going to have is a simple feature, so when we turn the console on, the lights won't be on. And when we say hold start and select for 3 seconds, the lights will then come on. So you have a nice, cool, soft on and off feature for the LEDs. This at least allows me to teach you some electronics. So you're not as bored as just going, here's an LED, plug it into power and it lights up. And it's also not as complicated as MCU code. So our basic ones is going to be creating an LED board with a soft on-off feature. Normally, I would just simply design this circuit, order it, and produce it. But because I'm going to teach you guys how things are done, we're going to drop to breadboards. So these are cool little devices that allow you to prototype hardware. We've got some jumper wires, we've got some resistors, we've got an LED, and we've got some buttons. So all these are sold on the store, so if you go on RetroSix.co.uk, you can buy all these tools. We're going to use a bench power supply as well, which again, we sell that. So you can follow along and make this project along with us, or you can just simply watch me do it. So in this video, we first need to replicate what's going to happen on this board. We have buttons here on the console, the up, down, left, right, start, select, A and B, as well as the triggers. And in order to understand these working and mimic them on a breadboard, that's what I'm going to show you now. So we're going to replicate using these little push buttons on this breadboard exactly how the buttons on the GBA work. And then after that, we can use that to input it into our little soft on and off system. And it will all be done on this breadboard and it will all fully function. And then we can create that, and then we can turn this breadboard into an actual schematic, and then from the schematic, lay the physical parts down into a circuit board and make the product. It sounds like there's a lot of work, but there really isn't. There's a few videos worth of describing how to do this, showing you the operations, and then producing the final product. So let's jump in and let's get these tactile buttons working the same as the GBA console does. Okay, so we have here a Game Boy Advanced, and then we've got all the parts we're going to need to understand the buttons. So the first thing we want to do is let's just move the other parts out the way for a moment. And let's just focus on this Game Boy Advanced. So as we know, the LED boards are going to sit around here and come out slightly to here for where we want to put all the circuitry. The LEDs are going to sit just under the buttons, at the edge of the triggers, and on the two buttons here as well as this trigger. So putting the LEDs down is not a problem, and I'll show you how LEDs work in a second. But the thing we want to understand is we want to kind of soft on off, so when we hold these two buttons, the start and select for say 2 seconds, the LEDs turn on, and if you hold them again they turn off, so like a toggle switch. We're doing this, one, because it's quite cool, because then you can install LED mods, but they don't have to be permanently on. And you can turn them on and off with a soft mod, so you don't have to have a physical button. You're using the existing buttons. So the first step to that guide is to understand how these buttons work. So here's the CPU, which will read the button states. And this is digital. So most CPU, well, to be honest, all CPUs, all sort of ICs that are doing any kind of signaling, video signaling, running code. They're mainly digital devices, and that simply means they work on ones and zeros, so a high voltage or a low voltage, not sort of a middle voltage like audio, where audio is an analog signal that's a constant waveform. So for digital signals, they're always reading simply ones or zeros based on time and other factors that basically turn it into how things operate. So this CPU has, well, let's start even more basic. So here's the pads, say, for the up, down, left, and right. So we have two pads here. One is connected to ground, I believe, in this case, and the other is connected to the CPU, so it can actually read what's going on. But the side that's connected to the CPU is pulled to 3.3 volts. So the CPU will see when nothing's pressed, and when you press the button, by the way, all that happens is the little black circle on the rubbers is a conductive pad. So you can think of it like, a piece of metal, something that's conductive. And it shorts out when it goes over here and a circle comes down. It basically joins these two pads together. So it would have the same impact if I touch the tweezers over these two buttons. That would act as I'm pressing the button. It would also act the same if I blob solder over the two. But what's basically happening is this side of the pad that goes to the CPU is pulled high by a resistor, which if we look on the back, we'll possibly find a resistor linked to the pad. Or the CPU itself might have a resistor inside that pulls the line high. We could find that out by quickly looking at the schematic, but that's not really the point at the minute. The point is simply this pad that the CPU reads will read 3.3 volts, which is classed as a high, so a 1 in digital logic. When we short out the pad with the rubber, when you press the button, because this side is ground, it will pull low this side, and that's the way the circuit works. It's a very basic circuit, and it's called a pull-up resistor circuit, or just a pull-up resistor button. And I'll go through how these work, but it's a very basic principle to start with. And it's simply to enable a button to be high when it's not connected, and low when it's connected or pressed. So let's just see that on the multimeter. So if I just power this console first, let's just chuck 3 volts on this console. And the console's booted, there's the light. And now we can see here is the buttons. If I get my multimeter and touch one side to ground down here, or I can go onto the battery spring, and the other side to this side of the pad, you can see the multimeter's reading 3.3 volts. So this side goes to the CPU, one of these pins over here. And at the minute it's reading 3 volts. Now, if I was to short this, and I'm not sure if I can do this with one hand, let me see if I can sort of get this in a position where... Right, there's 3.3 volts. So you can see that. Now, if I try and short this pad out as if I'm pressing it with the rubber contact, you can see it's gone to ground, 0. Let go, it's gone to 3.3 volts. Press down, it's gone to 0. So this is how the button's working. And just to double check this other pad is going to ground, if I just change the multimeter to continuity mode and I have the other lead on ground still, you can see this side isn't joined to ground, but this side should be. So there's the ground. So this pad is ground, this side goes to the CPU, and when it's shorted out, pulls to ground. And that's how this button is working. And it's the same for all these other buttons. They're all pulled high, and when you press down, they're pulled low, which means all these pads will have, and this is just redundancy, so 2 of the pads are connected together, they're just the same pad. So you'll find that's ground, that's not, that's ground, that's not. So you have 2 pads that are ground, and you have 2 that are going to the CPU. They're just joined. And if you zoom in close, you can actually see the solder resist joining the pads. So you can see here, this solder resist going around and joining this pad, and these 2 going up here to ground. So hopefully that makes sense, and that's how the buttons are working. So why is that important for what we need to do? So, as mentioned, the plan is we want to be able to read the start and select button and do something in logic with that information, and in this case it's to turn the circuit on or off. So to turn the circuit on and off, you need either a physical switch. So if we took an LED and just applied power to it, so let's just move that out of the way now, and let's bring in some circuitry. let's just go through some more basics. So we have here a breadboard, and all a breadboard is, if we turn it, say, this way, you can see we have down either side a negative and a positive, and this doesn't mean they've actually got any negative or positive voltage on. It's simply this is where you'd normally use it. So all this line here where the negative shows, so this pin, this pin, this pin, this pin, all the way down the board, they're all physically connected. So underneath this plastic, this is just a metal strip all the way down. Same for the positive, it's just a metal strip all the way down. So if I connected something here, it's also connected here and here and here. So it just forms the ability to, say, insert an LED and insert the ground leg here. And now everywhere all the way down here, the LED is still connected to this ground leg. The same goes for the positive. But where it gets different then is when we get to these rows here. They're joined horizontally instead, and they're only joined in these 5s. So this one here, row 1, is connected on these 5 pins here. So all these 5 are just one strip of metal all joined together. This side is actually a different strip, hence why there's a break here. So these 5 pins are joined together. The same goes down all the board then. So these are joined, these are joined, these ones are joined here, these are joined here, and so on. So if we zoom out and you look at the whole board, the way you could envisage this is this entire row all the way down here on the positive, all the way down is one connection. This one is ground all the way down. Same for here, this is positive all the way down, negative all the way down. What typically happens is you'll take 2 jumper wires, so again, just wire to connect things, and you join the positive here to the positive this side. And now what's happened is all of this outer row and all of this positive row are all the same thing, they're all connected. So if we got the multimeters and touch continuity all the way through, if these are still on, let's test it. You can test here to here. Let me just use the legs of these components because the meters won't fit in. So if I just connect that, say, and that, so I can actually get access to the pins. If I now get the meters and I touch on effectively this pin here and this pin here, you can see they're joined. If I remove this join down here, they're no longer joined. So I hope that makes sense. It's a simple thing, but it can also trip you up. It tripped me up at the beginning many years ago when I first taught myself electronics. And I kept visualizing that either this row was connected because these go down the board. I presumed these went down the board. Or you forget that these going across aren't joined all the way across and that they're separated over here. So it seems really obvious, but for beginners, it can also trip you up. So just try and envisage this, if we were to look under here, as wires going down like this for the pos and the neg rails. And in the middle, we have a bunch of rows like this. And these are all the dots. So you can see these are like the dots going down, and these are the dots going down. So these are all connected, these are all connected, these are all connected, and so on. So hopefully that explains what the breadboard's doing. So now why do we have this breadboard? Well, we want to mimic what we've just seen on here. So because we want to read these buttons, we need to first replicate what's happening on these buttons. So we need to bring 3.3 volts into this breadboard, which we'll do using a bench power supply. And then we need to pull a button. So another thing we need is a button, effectively, something that is 2 pins and disconnected when you're not pressing it and connected when it is. So here is such a thing. This is a tactile button. And if we get the testers again, we can see that you'll see the button has obviously 4 legs because you can use 2. It's effectively got 2 poles. But between them, you can easily test a button. I'll just move that out of the way a second. So in continuity mode, we can test from here to here. And you can see it's not connected. But if we turned it this way, for example, these legs are connected. So we have, if we turned it upright, these 2 pins are always connected. These 2 pins are always connected. And then they join with each other when you press the button in. So we know that these legs are joined and these legs are joined. So we need to split this way. So if we went to the board and we put the device in this way, because most devices are designed to fit in a breadboard. So if we push this in, like this, we can now see what we've done is added 4 pins. So now this pin here is connected to all these pins. So we can now break out and make a circuit from here when it's talking about this pin. The same for this. This now comes out here. This side comes out here, and this side comes out here. So if we get the testers again to see what circuit we're dealing with, if I touch here and here, you can see they're connected because already the switch is internally connected there, and the same for the top. So what we now actually have is this entire row 1 is all joined together, and this entire row 3 is all joined together. But when we press the button down, it will join row 1 to row 3. So that would then mimic having, say, this is row 1 and this is row 3. And when we press together, row 1 and row 3 are joined together. So let's just test that. Let's touch on, say, this side, row 1 and row 3, and you can see they're not connected together. And if I press the button, they're now joined together. So we have a basic button there, but the button isn't pulled up. So let's presume this top row 1 is the 3.3 volt line here that goes to the CPU. So we need to have the top of this button pulled to 3.3 volts. Now you think you might be able to do that if we bring in ground and 3 volts here, or 3.3 volts, that you can just do a wire like this and connect it up to the 3 volt line like this. Now you can do that, but the problem is the other side, and let's just use the red wire for example. If we were to pull this side to 3 volts and the bottom wire here, so row 3 to ground, when we press the button in, there's no resistance in this circuit. So what's going to happen? Well, there is technically a minute resistance in the wire in essence, but you have what's called a dead short here. What you're doing is taking the power supply and just joining both pins together, and that's a dead short, and that will cause a lot of heat, potentially blown fuses, all other kinds of bad things you don't generally want to happen in a circuit. So let's just bring in these breadboard wires. So again, we sell these as well as the breadboards and other parts, and you have a bag full of all these little bits, so all these little wires. And if you get them out of the bag, you have various sizes that fit across the breadboard to make a nice easy circuit that's neater than using big fly wire. So for example, if we took one of these blue and we brought in the circuit, we want to join the bottom pad, so in this instance row 3, to ground. You can see if we put the blue in, the blue isn't going to span over at all. It's not long enough. So we don't want blue. So we just pick another colour. So we'll pick one of these greys. And you can see the grey is the right length. So we can go from pin 3 there to ground here. Now, because I normally bring power in at the top, we probably want to move this button down a little bit to give us a bit of room to bring power in. And now we have pin row 3 and row 5 instead. So let's now move down to row 5 and connect him to ground. We could do it this side as well. It doesn't really matter which side you do because it's actually connected through the switch already and it's making a circuit both sides. But the bottom of the switch now is grounded. So now the question is, how do we enable 3.3 volts on one side of the switch, and when we press the button it grounds to 0 without dead shorting the power supply? The simple answer is through a pull-up resistor. Now there's nothing special about a pull-up resistor. A pull-up resistor is just a resistor. We call it a pull-up resistor because of how it's used. So if we just get a radial resistor, I've got a 10k here, and again we sell packs online, you typically have a pull-up resistor value anywhere from 1k to 100k. The more resistance, the less power you waste. But for this example circuit, I'm just going to use a 10k resistor. So bend the legs like this, and I'm going to go from what will be 3.3 volts here to the top of the button. And just make sure they're pushed in, because the resistors have a tendency with having thinner legs to sometimes come out of the breadboard or not make contact when you think they are. So I'm just going to do that. And now you can see we have a resistor on the plus going through into the switch, and then the other side of the switch going to ground. So when we press the button, we'll end up with a circuit that resembles this. So we would have a 3.3 volt circuit drawn like this. This is a symbol for a resistor, at least a really badly drawn one. And then going to ground, which is a symbol like this. Now, the button is technically sat here, and when we press it, it joins. So you would actually draw the circuit itself that we just made more like this. We have the resistor, then we have the switch, and then we have the wire that goes to ground. So this is the circuit diagram we effectively have here. When we push it, this joins, and you simply have a resistor going to ground. So this will make a perfect circuit to demonstrate, one with a multimeter and then two with an LED. So you can see it just visually working when you press a button. So on that note, let me just get the positive here, the negative here. And all I'm going to do now is get this bench power supply, set it to 3.3 volts, and I'm just going to join ground here, positive here, and pressing the button does nothing visually. However, if we get the multimeter, we can now check. So if we zoom in on this, if we now touch here, you'll have the voltage coming into the system, which you can see as 3.3 volts, which means the button, this side as well, because it goes through, is 3.3 volts, because if you remember, both sides of this, so row 3 is connected right the way through. So as well as this side here, it will be this side here. So we have the 3.3 volts, just like in the actual circuit now. So we've got the exact same situation here, the 3.3 volts that appears. And this side is simply ground, so we'll never see anything here. So pressing the button, this is always going to be ground at the bottom. However, the top now, which is simulating the left button of the Game Boy Advanced, if we were to press the button, you can see it drops to 0. Let go, raises up. So now we have a push button that acts just like the Game Boy Advanced. And this is a really basic circuit, and it's a very common circuit. And you'll find this is how a lot of buttons work in consoles. So now we have a button that simulates the Game Boy Advanced. Let me just show you an LED, and let's just show you how LEDs work. So LEDs are really basic. They are current-driven devices. So what that means is you can power LEDs from 1 volt, well, not 1 volt, because they have to have a certain voltage to break down. So different color LEDs break down at different voltages, which simply means they have to have at least a certain amount of voltage in order to work. So red LEDs are typically just under 2 volts, blue LEDs are 3 volts, white LEDs are 3 volts, an approximation. But after you get past the breakdown voltage, the LEDs are current-driven devices. So that means we could limit the current through this LED using a resistor like this, and the voltage then in excess of the required voltage doesn't matter. So we could power this LED from 10 volts, 100 volts, 1000 volts, it would still light up. The only issue we would get is when the voltage is that high that inside the LED it would cause an internal short between those two metal pads that you see, or potentially arcing, which then destroys the LED. So LEDs aren't voltage driven. There is no LED that is 12 volts. It's simply that whenever an LED system is made, they typically add a resistor that works at the right voltage to limit the current correctly. But in theory, LEDs can be driven by almost any voltage. The LEDs in this case, the long leg is nearly always positive, and the shorter leg is ground. So if we were to just connect this LED between ground and positive here, there's no resistance in line, so it's going to burn out the LED very quick, unless your power supply is limiting the current. But in this case, if you see the circuit we have a resistor here already. So we have a resistor from positive through to this leg and then down to ground. So what we have is we have ground here and we have a 3.3 volts here, but through a 10k resistor, limiting the current that's capable of being provided at this point. So we could just get the LED and put it positive side into row 3 and negative side into row 5. And you can see the LED light up. So there we have now an LED that's resisted with a 10k resistor. What we could do then as well is, instead of using this path to ground, we could remove this wire and put the LED directly in line with the positive side going to here, because ground starts here. You want the positive side to go up through the switch and to 3 volts. So if we put the negative of the LED to negative and the positive to the 5 volts, what will happen now is when we press the button, the LED lights up. And that's because the circuit we had here is simply now the same again. We have the 10k resistor, but now we have the LED, which is this symbol normally, and then ground. So we have the red wire here, the 3.3 volts, a resistor, then the LED, and then ground, and this is what's happening to light up the LED. So if we were going to make an LED board now, and that's all we were doing, so it just turns on when you turn the console on, all we'd have to do is solder to 3 volts, add resistors for each LED, and solder the other side of the LED to ground, and that's it. So that would mean on a GBA, for example, if we wanted to light all these buttons up, all we would have to do is pick up on the 3.3 volt line, which is here, I believe, next to VDD3. So here's the 3 volt line. And as I mentioned, some LEDs only just about break down at 3 volts, so you'd probably want to pick up the 5 volt line, which is here instead. So you'd solder resistors from here, and then the other side of the resistor would go to the LED that's, say, sitting here, and the other side would go to ground, which is, say, here, and the LEDs would come on, and that's the circuit done. But as I mentioned, that's fairly boring and doesn't really help us. So instead, what we're going to do is we are going to take this circuit. So if we just put this wire back in now. We're going to take this circuit, we're going to duplicate it again, because we have 2 buttons, start and select. So let's add another one. Let's grab another grey wire. Let's join that one to ground. We need another 10k resistor, pull-up resistor. And we want to send that one to positive, so let's keep them the same. So there's some nice symmetry. Let's move them up and out the way. So here's the current circuit. And now in terms of reading those values, so again, if you think of it as the circuit, we now have, say, let's go to what we're actually looking at, which is the start and select. We now have the start and the select buttons, or the equivalent of, in the circuit here, so this row and this row. So basically the top of the buttons. So if we bring them down ready for the next stage, let's just get, say, a red wire, and you read the top side of the circuit. So let's do this, say. You're reading the top here where the resistor is, because the other side is ground, so it's always going to be ground. So I'll explain more about general hardware and how things work as we progress. But just remember that you tap off at this point where the resistor is. This is how you work with a pull-up resistor. So this point here, if we read it, will be 3.3 when not pressed, ground when pressed. Now we've bridged this down to here, which now means row 14 is 1 pin. So let's call this select. And we also want the start pin. So we'll bring the start pin down to the row below it, say. So let's bring down a yellow wire from this pin to here. That's a bit short actually. Let's do a blue. So let's do a blue wire from that pin, and there we go. It comes down to the pin next to it. So now, keeping the circuit nice and neat, if we were to get the multimeters again, and if I was to touch ground on the ground wire, and I was to touch here now, you can see we have the 3.3, and if I was to press the button, we have ground. So here's a nice new connection point out the way of all the circuit that we can tap off for the start button, and the one next to it is the select button. So what we have now is a nice clean setup that's mimicked the start and select button of the GBA. And what we want to do next is we need to read these two low buttons, and we want both buttons to be pressed. And the reason for this is, obviously, in game you press start and select. In game you might accidentally press start and select together. So there's two things we need to do. The first is to only do something when both buttons are pressed, and the other one is we want to add a delay to when you press the button. So there's a few things we need to overcome. But the next step will be we will read in these buttons and we will pass them through an OR gate or a NOR gate depending on how we want to do the circuit. And what that simply means is we have two inputs at the minute that are both high or low. And we really want one input because we're going to have a digital circuit and we only care about are both buttons pressed, yes or no, so 1 or 0. At the minute we have two inputs. So if you use an OR gate or a NOR gate or an AND gate, there's lots of different gates, you can convert multiple inputs to a single output depending on what happens. So if we were to use what's called an AND gate, it would mean the output, the single output of an AND gate, would only be true if both the inputs are true. Hence AND. Both of them have to be the same. 1 and 2 inputs have to be the same. An OR gate means either or. So hence, if one or the other is high, the output's high. There's a NOR gate, which is an inverted OR gate, but I'll show you these in the next video. Due to the way the next step of the circuit's going to work, we want a positive, so a 3.3 volt, when both buttons are pressed. So we need a NOR gate because when one is pressed or the other is pressed or both are high, we want it to stay 0. Only when neither are pressed, so both are 0, we want it to then be high. You can see how these gates work, these logic gates, by just simply searching logic gate truth tables. And you have various gates. They're fairly easy to understand, but I'll explain the NOR gate in the next video. And we'll convert these two inputs so that when both are low, we have one single high output. This will allow us to then go, right, we have a high output. Now all we need to do is delay. We want that output to be high for, say, 2 seconds or close to 2 seconds before we turn the gate high. So we need to slow down the signal where we have to wait and they have to stay at that value before we trigger a true digital high value. At that point, we can then turn the system on, and then we'll figure out how to do exactly the same, hold it again to turn the system off. So I hope you're learning a little bit about circuits and how we're putting them together on this breadboard, and that this really basic circuit makes sense. And in essence, we've just made an LED circuit. If you wanted to make a conventional LED mod for the Game Boy, you could do it now with nothing more than this circuit. But this is where we want to add that little bit of logic to make it fun. So I hope you enjoyed that, and I'll see you in the next one.